Welcome to Lecture 2.6, Singular Points and the Frobenius Method. Let me summarize what this lecture is about before we begin. So in the previous lecture, we learned about how to solve certain ODEs with the power series method. So we assumed that the solution had the form of a power series. We plugged back in and solved for the coefficients. We found a recurrence relation. Now this doesn't always work. There are some subtleties, particularly when there are these so-called singular points, which we'll learn about in this method. In that case, we need what are called generalized power series, and solving ODEs using those is sometimes called the method of Frobenius, or the Frobenius method. So let's get started right away. Let's begin with a quick review of power series. This is not going to be a focus of the class or even this lecture, but you need some basic terminology before we begin. So a power series, first of all, it's centered at a fixed point x naught. You can always, for this lecture, just imagine x naught is 0. But just know that it could be something else. It could be like 2. So what a power series centered at x naught is a limit of partial sums. So we write it as an infinite sum like this, but what we really mean is we're taking a finite sum from 0 up to capital N, and then we're taking the limit of those finite sums as n goes to infinity. Because technically we don't know what an infinite sum is, but we can define a limit. This series converges at x if the sequence of partial sums converge. So we define what it means for a series and infinite sum to converge based on whether this sequence converges. This should be familiar from your Calc 2 class. If it doesn't converge, then it diverges. So in this lecture, in this class, we're not going to do things like ratio test, root test, but just know that they are out there and you could apply them if needed. Here are some simple examples. So here's a power series. This is the infinite sum from 0 up to infinity. Formally, we write as a limit of partial sums of 1 over n factorial times xn. This converges to e to the x everywhere. So we say for all x. So this function literally equals e to the x everywhere on the real line. In contrast, the series here, so you can think of this as the infinite sum from n equals 0 to infinity of negative 1 to the n, x to the n. So what this is 1 minus x plus x squared minus x cubed plus minus etc. So this actually is equal to a function in the open interval negative 1 to 1. It doesn't make sense to plug in 1 or 2 or 3 or anything else, but it actually does converge to this fraction for all x in this interval. It diverges at x equals 1 and outside this interval as well. Here's a quick definition. The radius of convergence is the largest number r such that if we are less than distance r away from the center of the power series, then it converges. So I think this is best just seen with a simple example. So let's consider the power series up here, or even easier, consider the following power series, which is n equals 0 to infinity of x to the n. So this is 1 plus x squared plus x cubed plus etc. This is equal to 1 over 1 minus x, but only for x in negative 1 to 1. Otherwise, obviously, you plug in any other number, this thing is not going to converge to anything. It's going to diverge. So at the real line, we say that if this is 1 and this is negative 1, then the power series converges in this interval. So we can always define the interval of convergence, and then the radius of convergence is just the radius of this interval. So in this case, we say that r equals 1. So basically, we look at where the power series is centered at, and we see how far can we go out from there and ensure that the power series is going to converge in that interval. That's all this is saying. So you can think of it as how big of an interval does this thing actually make sense? Is it defined? One more quick definition. A function is real analytic at a point if it has a power series representation at that point. For all intents and purposes, you can think of real analytic as having a power series, or if this thing is defined. Now, there are slight technicalities. There are functions out there. You can Google bump functions if you want. You can construct these weird functions that are are like this, and they are so flat at x equals 0 that they don't have a Taylor series representation. What I mean by this is if you can try to compute the nth Taylor coefficient, you're going to get 0. So these things are so flat at 0 that they are indistinguishable from the 0 function at x equals 0. They exist. They're not natural. For all intents and purposes, when I say a function is real analytic, I just mean, is it defined? Plug in x, does it actually equal anything? Now, we need one more definition. And I'm going to go through this whole thing without explanation, and then I'll give you an example, and I think it should fall into place. So let's consider a second-order homogeneous ODE. So y double prime plus p of x y prime plus q of x y equals 0. We've seen these things before. The point x naught, again, you can picture it to be 0 if you want, is an ordinary point if these functions are analytic at x naught, real analytic. In other words, if they're defined. Otherwise, it's a singular point. And now there's two types of singular points. We say a singular point is regular if these modified functions are real analytic, if x minus x naught times p of x, and x minus x naught squared times q of x are analytic. Otherwise, it's irregular. Let's do 3 quick examples, and I promise this will be a lot clearer at the end of these. So for all of these, I'm going to consider the point x naught to be 0. So we're looking at power series centered at 0. So I claim that 0 is an ordinary point in the following ODE, and here's why. So this here is p of x, and q of x is 1. Q of x equals 1. Both of these functions, p of x equals x and q of x equals 1, these things are real analytic at 0. They are functions that are defined at 0. Functions that are going to fail to be analytic are like when we're doing 1 over x. So these have power series representations. You're looking at them right here. There's just one term. Okay, the second example, I claim that 0 is a regular singular point at this equation. So here's why. So we have to write this equation in this form. And the key here is y double prime is monic. So we have to write this equation as y double prime plus, now x over x squared, that's 1 over x, y prime, plus 1 over x squared, y equals 0. So now this is p and this is q. So p of x equals 1 over x and q of x equals 1 over x squared. These things are not defined at 0. They are not real analytic at 0. You plug in 0, you don't get anything. However, so 0 is a singular point. Now, is it regular or irregular? Well, here's what we have to check. We have to consider these two functions and see if those are defined at 0. So now, let's do x p of x, and this is 1. And then the next one is x squared q of x. So we're testing this x minus 0 squared q of x, and that equals 1. Both of these are defined at 0. So therefore, this singular point is regular. Okay, here's a non-example. So I claim this is 0 is an irregular singular point at this equation. Let's see why. So let's do the same thing. Y double prime plus, now we have 1 over x squared, y prime plus 1 over x squared y. Once again, this is p and this is q. So p of x equals 1 over x squared, and q of x equals 1 over x squared. Well, the next thing to do is to check x p of x. That's 1 over x. That, supposed to be an x, that fails. That is not defined at 0. Therefore, this is an irregular singular point. Now it turns out that x squared q of x is defined as 0. It doesn't matter. This thing breaks down. So this is an irregular singular point. Again, this is regular this is a singular point because these weren't defined at 0, but we can fix them and they are. This is an ordinary point because we never had a problem in the first place. Both of these P and Q were defined at 0. Here's the main theorem of the lecture. It's called the theorem of Frobenius. So consider an ODE, just like we saw in the previous slide, except now suppose that it's inhomogeneous. So the forcing term, let's call it f of x. If x naught, again, you can always think this to be 0 in this lecture, is an ordinary point, and suppose that p of x, q of x, and f of x have radii of convergence, let's call them rp, rq, and rf respectively, then there's a power series solution of the following form. And the radius of convergence of that power series is the minimum of these 3 radii. So basically, here's how I think of this. So again, pretend this is 0. It says, let's suppose that p of x, so p of x is a power series. It doesn't have to be defined everywhere. Let's suppose that p of x is defined in here. So this is rp. Let's suppose that q of x maybe is defined in this range. So this is rq. And suppose that r of f is defined in this range, r of f. This result says that there will be a power series solution, but it's only going to be defined in this smallest interval. Now, if f breaks down outside of here, we can't expect that our solution to exist outside of here either. So that's all this is saying. If we have an ordinary point, there is a power series solution. And this is just a technical detail about the radii of convergence. Next, if x naught is a regular singular point, and these 3 functions are almost the same, instead of p, q, and f, it's x minus x naught times p, x minus x naught squared times q, and f have the same 3 radii of convergence, call them rp, rq, and rf, then there is a generalized power series solution of this ODE. So what is a generalized power series solution? Well, it is a power series, except it has this extra term in front of it, where r is some constant. Now, r could be a negative number, it could be a fraction, it could be complex. So let's think about what this actually means. So suppose we have n equals 0 to infinity of a n x to the n, and we have, suppose r is 1/2. We have x to the 1/2. And then what does this look like? So this is a naught x to the 1/2 plus a1 x to the 3/2 plus a2 x to the 5/2 plus etc. Is this a power series? Well, technically not how we defined it, but you see what it is. It's a power series times x to the square root of x. Or, we could have something like r equals -1, in which case we have x to the -1 times a power series. And this is going to be a naught times 1 over x, or x to the -1, plus a1 plus a2x plus a3x squared plus etc. Again, is this a power series? Well, it's not really defined at 0. It has this negative term out here. There's negative exponent, but it's a power series times x to the -1. So that's what a generalized power series is. And to summarize this, if we have an ordinary point, we have a power series solution. If we have a regular singular point, we have a generalized power series solution. If we have an irregular singular point, all bets are off. We aren't guaranteed anything. And notice this is not saying there are 2 generalized power series solutions. This is saying there is one. Now, we know that the fundamental theorem of linear ODE says there are 2 linearly independent solutions. I'm not guaranteed that there's going to be that this method is going to produce a second one. This method that I will show you, plugging this back in and finding n and finding r, will give us one of the solutions, but then all bets are off for how to find the second one. And more often than not, you can find the second one. Like, this will work. However, there are some special cases, especially when we look at Bessel functions and Bessel's equation in the very next lecture, where we actually only get one solution via this method, and we have to do some algebraic tricks to get the other one. So here's an analogy of how I like to motivate what this is saying, like the difference between an ordinary point and a regular and irregular singular point. So let me give you three functions. So let me say f of, really simple, f of x equals x. This function here, this is defined at 0. It's supposed to be at 0, right? It's defined at 0, no problem. I'm going to say 0 is an ordinary point of that equation. Okay, here's a slightly harder one. F of x equals x squared divided by x. Yeah, what about this? Well, if you plug in 0, if you say, well, f of 0, if you don't reduce it, you write 0 over 0, technically this is not defined. So if in like middle school or high school, you learned if you were to graph this, you got to put a hole there at 0, and otherwise a function looks like this. So this is a singular point. It's not defined, but it's fixable. We know what it should be. However, if we say f of x equals 1 over x, now this is a singular point as well. It is completely unfixable. There's really no way to define what it should be at 0. So as an analogy, think of this as an ordinary point at 0. It's defined. This is a regular singular point at 0. It's not defined, but we know what it really should be. And this is an irregular, unfixable singular point. So it's not a definition of these, but that's an analogy that really does carry over well. Let's do an example. So let's find the general solution to the following ODE. This is a second order homogeneous equation. 2x y double prime plus y prime plus y equals 0. Okay, so just for good measure, let's divide by 2x, so we make this monic. So y double prime plus 1 over 2x y prime plus 1 over 2x y equals 0. So this is p, this is q, in other words, p of x equals 1 over 2x. This is clearly not defined at 0, and nor is q. q of x is 1 over 2x. So 0 is a singular point. However, if we compute x p of x, this is 1/2, and x squared q of x equals x over 2, then both of those are defined at 0, so this singular point is indeed regular. So that means that we can find a generalized power series solution. So that's y of x is n equals 0 to infinity a n x to the n plus r. Now I like to put the r inside. I strongly recommend doing that. It just makes it easier when you take the derivative. So let's take derivatives of this. So y prime of x equals n equals 0 to infinity of n plus r a n x to the n plus r minus 1, and y double prime of x equals n equals 0 to infinity of n plus r times n plus r, not plus, that should be minus 1 times a n times x to the n plus r minus 2. Now let's plug these back into the ODE. Now it's always easier to plug it back into the original one. We don't want to be dividing by x's here. That's always bad news. Trust me on this. So okay, let's write this out. So 2xy double prime. So this thing here, let's put a 2 in front, and let's make this r minus 2 and r minus 1. So that is n equals 0 infinity of n plus r. Well, I almost forgot my 2. 2n plus r times n plus r minus 1 times a n times x to the n plus r minus 1 plus, the next one is y prime. So y prime, that's n equals 0 to infinity of n plus r times a n times x to the n plus r minus 1 plus y, so that's this term, plus n equals 0 to infinity times a to the n, or a n x to the n plus r equals 0. So now let's, first I'm going to combine these two terms, because these things, actually even before that, here's what I'm going to do. I'm going to factor out x to the r, because we have that in everything. We don't need that. So I'm going to factor out x to the r. Now I'm going to combine these first two terms, n equals 0 to infinity. Now what's left? So let's see, we have a bunch of n plus r's here, and we got one n plus r here. So how many n plus r's do we have in this first term? So we have a 2, and we have times 2n, n plus r minus 1. So we have 2n plus 2r minus 2. That's how many of these n plus r's do we have. And over here, we have 1 n plus r. So this is 1. So together, we have 2n plus 2r minus 1 n plus r's. So that's 2n plus 2r minus 1. We have that many n plus r's. And then we have an an, and we have an x to the n minus 1, because we took out the x to the r. Now in this term, we have n equals 0 to infinity of an x to the n. And we need to set that equal to 0. So we need to combine these terms. We can divide through by this x to the r. We don't need that anymore. We want to So we want to combine this into a single sum and set the coefficients equal to 0. So let's shift the indices. So we can do that by letting m be equal to n minus 1. So we want n to be equal to that. Let's call it m. And then, in other words, n is m plus 1. And so what we could do is we could turn this into an m, then each n becomes an m plus 1, then we could change m back to n, like we did in the last lecture. But if you remember, basically the net effect of this is each instance of n turns into an n plus 1. So let's just do that. So this is n equals, I'm actually not going to write down, I'll leave this blank just for a moment. N equals something to infinity. Think about what that should be. And so now I have a 2 n plus 1 plus 2r minus 1 times n plus, so this becomes n plus 1, so n plus 1 plus r. We have an a n plus 1, we have an x to the n, and then the next term we haven't touched is n equals 0 to infinity, a n x to the n equals 0. Okay, so now let's simplify this a little bit. What's this first term equal to? This is, well, actually, before we do that, let me say what's here. So you remember the last lecture how I said this really should be a negative 2, but I made it 0 because those first two terms go away when we take derivatives? Let's revisit that. So if y of x, we're up here now, if y of x equals a naught plus a1x plus a2x squared plus a3x cubed plus etc. Now if we take a derivative of this, what happens to that first term? It just goes away. So we get a1 plus 2a2x plus 3a3x squared plus etc. Again, that goes away because the derivative of x to the 0 equals 0x to the minus 1, and so forth. However, if we have a generalized power series, now in this case we have something like this. We have y of x equals, suppose r is 1/2. So then we have a naught x to the 1/2 plus a1 x to the 3/2 plus a2 x to the 5/2 plus etc. Now if we take a derivative, that first term is 1/2 a naught x to the minus 1/2. And that no longer goes away because r is a fraction. So we cannot assume that this this first term here when we take a derivative of that, that's going to go away. So this, even though this r is pulled out and it's no longer here, this n minus 1, we can't can't ignore it. So I'm going to put a negative 1 here. And if you want to see why that is true, notice that here when n is equal to 0, that's the same thing as when m equals negative 1. So we're starting at negative 1, and now we want to combine these terms. And there's, well, the x to the n's are okay, but now there's one problem. There's this extra negative 1 term here. And let me show you over here again what we have to do with that. So let's add two sums. Suppose we wanted to add n equals negative 1 to 3, x to the n, plus m equals 0 to 3 of y to the m. Well, now what is that going to equal? So that's x to the negative 1 plus 1 plus x squared plus x cubed. And then plus, well, we're starting at 0 now, so plus 1 plus y squared plus y cubed. So when we add those guys up, we get x to the negative 1. We can't really write this in a sum because we got that lingering term, so we have to pull that out, and now we can write this as a sum of n equals 0 up to 3 of x to the n plus y to the n. So I don't know why I called this m. That would have been just fine to call it n. Doesn't matter. Well, I guess it shows you that really the dummy variable doesn't matter. So the point is, we got to pull out this extra term. We have to pull it out before we can combine these sums. So this n equals negative 1 term, so what is that? Well, first of all, let me slightly simplify this. So this is 2n plus 2r, and then there's a plus 2 in here and a minus 1, so plus 1. That's what this really is. And this here is n plus r plus 1. I'm going to put the 1 at the end. Okay, so the n equals negative 1 term, that happens. So let's plug in negative 1. So this 2n plus 1, that goes away, and we are left, and this n plus 1 plus r, so this is, so when n equals, when n equals negative 1, again, this term goes away, and we're left with a 2r minus 1 times an n negative 1 plus r. So we are left with 2r minus 1 times r times a to the n plus 1 when n equals negative 1 is a naught times x to the negative 1. So that's the n minus 1 term. And now I can add up the rest. So now I have n equals 0 to infinity. And what do I have here? So let's see. So I have a 2n plus 2r plus 1 times n plus r plus 1 times a to the n plus 1 plus a to the n, and I'm going to factor out an x to the n and set that equal to 0. Okay, so now what does this tell us? This is a generalized power series. If this is equal to 0, then it must be the case that this has to be equal to 0, and it also must be the case that this term is equal to 0. Now, a naught is not guaranteed to be 0. We can set that to be anything we want to. So, and x to the minus 1 is not 0 either. So we have to have that this guy is equal to 0. So what this tells us, so first of all, this is called sometimes this equation in R is called the indicial equation. I guess that's from indice. I didn't name it. I don't really call it that. But you might see it around. So this tells us that 2r minus 1 times r equals 0. And so that tells us that r equals 1/2 or r equals 0. Tells us what r can be. R equals 0, that's a regular power series. R equals 1/2 is a generalized power series. So that's good. That tells us what r has to be. Next, we have this is our ordinary recurrence relation. So if we set this equal to 0, let's see, so now we get a n plus 1. So I'm going to solve for a n plus 1. So that's equal to, so I'm going to move that to the other side of the equation. So set this equal to 0, solve for this, and I'm going to get, oops, I switched colors there accidentally, equals negative 1 over 2n plus 2r plus 1 times n plus r plus 1 times an. So this is my recurrence. Is it en or I think it's en? Our recurrence relation, and this is what r has to be. So notice that we have two generalized power series solutions. So we have two generalized power series solutions. Sorry, I didn't write that too clearly, but I think you know what I mean. So we have one where r equals 0. In that case, we have r0 of x equals infinite sum from n equals 0 to infinity. This is an ordinary power series. an x to the n, and now our recurrence relation, let's just plug in r equals 0 into here. So we get that a n plus 1 equals, well, on the bottom of the fraction, let's do that first. That's 2n plus 1 times n plus 1, and then we're negative 1 times an. So there's one solution. And the other one is when r equals 1/2. And now we have y, let's call it 1/2 of x equals x to the 1/2. Well, that's just the square root of x, if we can write it like that, times this power series, n equals 0 to infinity, an x to the n. And now we have a recurrence an plus 1. I'm going to plug in 1/2 in for here. So this becomes a 1. 2 times 1/2, that becomes a 3/2. So we have, this is equal to negative 1 times 2n plus 2 times n plus 3/2 an. So these are our two solutions. So if we wanted to, we could analyze this more, and we could, fix a naught here, and then write a formula for a1 and a2 and a3, and write up a general formula. We could do that. I'm not going to do that. I don't think we need to. I wanted to do it once for you last lecture and not again. And we could do the same thing here if you wanted to. But these are two distinct solutions. It is not clear that they are actually linearly independent. It seems like they really, really should be, right? How could these possibly be scalar multiples of each other? Don't worry, they are. But there are some cases with Bessel's equation, as we'll see in the next lecture, where you have a power series and a generalized power series, and they do not look like they should be multiples of each other, but they secretly are. So in that case, this method only gives us one solution. It's only guaranteed to give us one solution. But here, the general solution, let me write it like this. So the general solution, so what we could do is, well, I guess just our constant is sort of embedded in here, the a naught and the other a naught. But our general solution, one way it's a little bit sloppy, but we could write it as y of x equals c1 y naught of x plus c2 y to the 1/2 of x. And maybe we could, if we set the a naught equal to 1, then here are those constants. But regardless, even if we have extra constants embedded in here, every solution is of this form. It's a linear combination of these two guys. So notice that this is different from the power series that we saw in the last time. Here we had recurrence an plus 1 in terms of an. So it wasn't every 2, it was every 1. So we fix a naught, everything is determined, but we have two different power series in this case. So it's different. We still have two solutions, but it's just a little bit different. Let's conclude this lecture by discussing a few applications of this Frobenius method. This comes up all over physics and engineering, especially physics. So here are some examples of, I guess we saw this a little bit in the last lecture, Cauchy-Euler equations. These are equations like this. X squared y double prime plus ax y prime plus by equals 0. These things arise when solving Laplace's equation in polar coordinates. Next is Legendre's equation. We actually solved this in the last lecture, and we will see it in a couple of sections later. We study Sturm-Liouville equations. We'll actually see a lot of these in that section. So Legendre's equation is 1 minus x squared times y double prime minus 2x y prime plus n times n plus 1 times y equals 0. And this is used for modeling spherically symmetric potentials in the theory of Newtonian gravitation and electricity and magnetism. Basically, it's when you want to solve Laplace's equation not in polar coordinates, but in spherical coordinates. So anytime you have a physics problem and it's spherically symmetric, Legendre's equation is bound to come up. Next is Chebyshev's equation. This is similar, just the only difference is instead of a 2x here, you have an x. Instead of an n times n plus 1, you have an n squared. This arises in numerical analysis techniques. Hermite's equation. This looks simpler, but it's actually going to be more complicated when it comes to Sturm-Liouville theory. Y double prime minus 2xy prime plus 2ny. This is used for modeling simple harmonic oscillators in quantum mechanics. There's Bessel's equation. This is the topic of the next lecture. This is x squared y double prime plus xy prime plus x squared minus n squared y equals 0. We'll also see this in a later lecture on Sturm-Liouville theory. And these things are used for analyzing vibrations of a circular drum. Let's go back to Laplace's equation. You'll learn more about that later. But if you solve Laplace's equation in polar coordinates, I said Cauchy-Euler comes up. Actually, the general ones that come up are the Bessel functions, or the Bessel's equations, and the solutions are Bessel functions. So again, the whole next lecture is going to be on this equation. Finally, I don't even know how to say this. I've read it a lot. I guess it's Laguerre's equation. Sorry if I pronounced that wrong. That's similar to these. And this arises in a number of equations from quantum mechanics. If you look at the wiki page, you see a whole bunch of them. I won't even try to summarize them because I can't even pretend to be a physicist. And finally, Airy's equation. Y double prime minus k squared xy equals 0. This models the refraction of light. So these things come up in physics all the time, and there's x's and not t's there because they're typically functions of positions. So y is a function of x. And we will see these a lot, well, some more than others. We'll see, again, Bessel's equation is the topic of the whole next lecture. We'll solve those because those will come up later when we look at PDEs that describe the waves in polar coordinates. Most of these we'll see later when we study Sturm-Liouville theory. That is, how do I describe that? That's a special way to see a second order view a second order ODE in a certain form. So you get these eigenvalues and eigenfunctions. You get infinitely many of them. And so what are those? Well, you see these n's here. Those correspond. Those are the eigenvalues of these equations, and there's one for each n. Think of them like harmonics or fundamental frequencies or fundamental nodes or modes. And so you have one for each n, and then you have a corresponding eigenfunction, and then the eigenfunctions are orthogonal. It's amazing with this inner product, and then from that you get these generalized Fourier series expansions. It's incredible. So it's coming up shortly. What else do I want to say? Yeah, let's for practice. Let's see. X not equals 0. Is this an ordinary? For each of these, let's see. Is this an ordinary or singular point? And if it's singular, I guarantee you it's going to be regular. Because if it's irregular, there just won't be solutions, and these things wouldn't be so well known. Okay, so Cauchy-Euler equation. Let's start out with this. Well, if we divide through by x squared, we get y double prime plus a over x y prime plus b over x squared y equals 0. And so this is actually a singular point. 0 is singular because you plug in 0, it's not defined at these functions. But this was a little bit of a misleading because you might think, oh, there's a generalized power series solution. But we know that there are solutions of the form y of x equals x to the r. So really, really simple functions. This, I guess it's a generalized power series, but it's a really stupid one. I guess it has to be because, yeah, so it's this thing times 1. So, yeah, 0 is a singular point here. What about Legendre's equation? Now, if we divide through by, I don't know how to write this. How about, let me do Chebyshev's equation first, just so I can, it's a little bit shorter. So Chebyshev's equation, let's divide through by 1 minus x squared, and we get y double prime minus x over 1 minus x, 1 plus x, times y prime plus n squared over 1 minus x times 1 plus x. And there's a y in there, equals 0. So x equals 0, is this ordinary or singular? Well, if you plug it into, it's defined. You plug in 0 into here, that's defined, and so is that. So this is singular. And so for the same reason, 0 is a singular point of Legendre's equation. So this is singular. Now, Hermite's equation, this is actually going to be pretty complicated. This is going to have a complicated, weird weight function when we study Sturm-Liouville theory. But it looks like a very simple equation, and 0 is defined for both negative 2x and 2n, so 0 is actually an ordinary. We're just doing this for practice. Point. For Bessel's equation, we got to divide through by x squared, so this is going to be singular. And in fact, we are only going to get one generalized power series solution for this, and the other one we're going to have to use reduction of order trick to get that. That's annoying. This Laguerre's equation, we divide by x, and it's going to be singular. And Airy's equation is going to be regular. Now, this isn't completely, this is a little bit misleading because Legendre's equation, or Legendre's and Chebyshev's equation are actually going to be defined on intervals are from -1 to 1. And so we're actually concerned about whether this, and so it might be of interest to express this as a power series centered at 1 or -1 or something, or not necessarily at 0. Remember this x equals 0, that's just the most common place to center a power series, but there are plenty of power series that are centered elsewhere. Okay, so these are fun. We'll see these again throughout the course. Especially, we'll do some before we do PDEs, but we do them then because they arise in PDEs. So basically, when we study a PDE, that's going to be this differential equation, it's a partial difference equation. It's going to be something like a function of two variables, u of x and t. This is the wave equation, and so you get partial derivatives, and when you solve these things, you separate the variables in time and in space, and the ones in space you get, for both of these you get ODEs, and these are the type of equations that you end up getting when you solve the variables in space. Okay, that's a preview. I hope you're excited. Stay with us.